Tech Nuggets, IPv4 routing part 2. In our previous video, we talked in broad general terms about how routing works and how data is packetized, and we use routers to push the data around the network to get it to where it needs to go, much like FedEx or a package delivery carrier would route packages through central hubs and then out to destinations. One of the things that comes up with this kind of discussion is how communication happens in a LAN. So I wanted to cover this a little bit. This is going to be one of those topics that we will cover in an additional video, but we're not going to talk about local LAN communication a lot. There's a different discussion going on at a frame level, which is a little lower than a packet level. Packets are actually inside frames, and at a frame level, we can communicate back and forth. And one of our examples, which we'll talk about here, there's a discussion about talking to a printer, which actually happens at a frame level. Even though the machines have globally unique IP addresses, we're not going to talk about that a lot. It uses ARP, which is a topic that's worthy of an entire video in and of itself, which, like I said, we'll cover at a later date. All right, so back to our example. We're going to go through the same examples, but we're going to put some more detail in it. We're going to put some IP addresses. We're going to talk about packets in a little bit more detail. And I just wanted to go over the kind of basics here again. We've got Kelly that has a globally unique IP address that's already been statically assigned. Kelly has the IP address of the local gateway Chris already programmed in, and Kelly knows the IP address of the local printer Zach. Those have already been put in the machine. They were put in manually by hand, so somebody walked up with a piece of paper and typed them in. On the slide there, I've got Kelly, Zach, and Chris's IP addresses and what they are. And we will add other devices as we go along through different examples, and they will come with their own IP addresses. If the IP addresses with the slash notation on them look concerning, like not sure what that means, make sure to refer to our earlier videos about subnet masks, subnet masking, and how to work with those so that you understand how big the networks are. Understanding subnetting is absolutely key to understanding routing. If we don't understand subnet masks and subnetting, we will not understand routing. We will be using that information heavily. It is a required concept before we can do routing. All right, so here I have an example that we saw earlier of our 3 machines in a local area network connected to a mini switch. And we've got Kelly with an IP address, and Chris with an IP address, and Zach with an IP address. And off to the left side, I've done my very best to give a visualization maybe of what a packet might look like. So at the top, we've got a destination address, and then we've got a source address, and these would be considered headers. And beneath that, we've got packet data or payload, depending on what word you like. And that's whatever data we're trying to send. In this case, it'll be a piece of whatever we're sending to Zach to print. And there might be thousands or millions of these packets that go from Kelly to Zach to recreate the print job after we packetized it and sent it across the network. All right, so I've gone in and added the IP addresses to the example packet so that you can see them. You can see the source is Kelly and the destination is Zach, and I've given a little more detail as to what our payload is, which in this case is a print job. Kelly will transmit to Zach. Zach will reassemble the print job out of all the packets and then print. Across a local network, it's not too tough to do. It's something we all do a lot when we're printing or transferring files or things like that. All right, before we get a whole lot farther in this discussion, we should probably have a discussion about what's a route table. A route table and a router, and there's a lot of similar words and they can be very confusing. So we're going to talk a little about a route table, and in this context, a route table is quite literally a text table, and that's the way we'll see it when we use Netstat or other tools that will show it to us. And it will be a list basically of networks, and then when I see traffic for that network, where do I send it? So you can think of it as sort of a short version of a menu of directions. If I was standing at a large intersection with many roads, and I was standing there looking at a list that says, when I want to go somewhere on the left side, which road do I take on the right side? And we talk about packets traversing the route table. Oftentimes, especially when you're standing at a crossroads, like I said, there are a lot of different ways to the same place. Some places are better than others. Some ways to get there are better than others. So as we traverse the route table, we try to find the, quote, most specific route to a destination. And we'll see that as we go through some of these examples. The router doesn't actually always know where to find an end destination. Every router in the world does not know where Google is. It doesn't work that way. What the router does know is, well, I may have a more specific route and I'll send it that way, and the net person on the other end should be in the right direction and they'll know who to send it on to. So a lot of times we traverse the route table and we're not sure what's exactly on the other end, but we know it's in the right direction based on the route table entries that we have a more specific route. At the end of the day, at the very bottom of our route, as we traverse a route from the route table from the top to the bottom, at the last entry in our route table is always the default route. When I don't know what else to do with a packet, what do I do with it? Well, we program in a default route. When you don't know what else to do with it, you hand it to the default route and it goes that way. When we looked earlier at Kelly's route table, Kelly had a default route. Don't know what else to do with it, we hand it to Chris, it left the network. Routers have the same function. When they don't know what to do with something and it doesn't match any more specific route, it goes out the default route. If you don't have a default route, you're going to be very careful about how you create your route tables, because there may be networks that aren't covered with no default route. Default route is often the very last entry in the route table, as it is the least specific, being default, least specific route you could ever have. Anything will be more specific than everything. All right, here you can see we've got an example packet that's got a source and a destination, and then we've got a sample route table. And you can see on the left side it says network, and we list a bunch of networks. And on the right side it says next hop, and in this case it's just giving Ethernet cards, NIC1, NIC2, NIC3, and our router in this case will have 4 Ethernet cards in it, and it'll be directly connected to 4 different networks. And when we look at that, we can look at our source, and we're not as worried about where it's coming from. That would be, a Kelly machine that's sending the machine. In our case, we're interested in the destination. So we're looking at that 99.11.57.3 number. And when we look at it, we need to compare it to the networks that we see on the left side of the table. Is that IP address in the first network? Is it part of that network? When we look at 145.6.55.0/24, is that IP address of 99.11.57.3 in that network? If it is, well, then we go over to the column that says next hop and we shoot it out NIC1, and that's the way it goes. That's a more specific route. In our case, if you look at that subnet mask, you'll realize that 145.6.55.0 is a /24. That means it goes from 0 to 255 in that range. And in fact, 99.11.57.3 is not in that network. So the router will skip that entry and go to the next one and do a comparison. It'll look at 202.245.165.0/24 and try to decide, is my packet in that network? And it'll evaluate it. And this one, in this case, the next 3 entries, our packet is not in any of those 4 networks. So it's saying, well, I don't know what to do with this. Where do I do with this packet? At the very bottom, we can see 0.0.0.0, which is our default route. In our next hop category, we can see there's an IP address given. We'll forward that packet on to that router. And 145.6.55.254 is a specific machine. It's not a network. It's a specific machine that is the default route for our router out. It's the next hop. It's how we pass that data on to the next person. And we hope that router has a more specific route for our traffic. And oftentimes we'll pass it up the chain several times before we get much closer to the backbone of the internet, where more specific routes will kick in. And we'll have an example that goes through this, but I wanted to go over just route tables and packets and how they might traverse a route table a little bit before we went on. We'll go on to our second example and add IP addresses, and I'll update the packet to have the IP addresses for source and destination in it, and we'll go through how the packet traverses the network to reach the corporate web server on the far end. So on the left here, you can see I've put the packet. It's got a source of Kelly, at 45.65.22.33, and we've got a destination of a corporate web server at 102.88.65.10, and in the bottom part you can see in our data we have a request for a web page. So the first thing that happens is Kelly will evaluate the packet and go through Kelly's route table. The first entry for Kelly's route table will look at the destination of the packet and try to match it with the first entry that comes along. Route tables are organized in most specific to least specific. So as we go down a route table, we're looking for the most specific route, and the routes will get more and more general as we go down the route table. When it hits an entry that it matches, it will go to the next hop part of the table and disappear. It will not continue traversing the route table. We'll continue until we find a route that matches, and it will go out, which leaves our least specific route at the bottom, which is our catch-all of the default route. Kelly will look at this packet, will evaluate that 102.88.65.10 is not part of the first entry. And if you'll remember from our subnetting video, that network is only 256 entries, so it'll go 0 to 256, and 102.88.65.10 is not in that range, so it will not take that entry. It will drop down to the default route, which will shoot it off to Chris. Now, Chris has a specific IP address, so we're going to forward the packet to Chris. Chris and Kelly are in the same network, so when you look at the route table and you see an IP address, you'll say, hey, that IP address is in the route table. It's in the network with Kelly, and Kelly and Chris must be in the same local area network for the forwarding to happen. That's how routing and forwarding works. Chris will receive the packet, we'll look at the destination, and we look at Chris's route table. Chris will begin to evaluate it against entries in the route table from the top to the bottom. And the first thing that'll happen is Chris will evaluate it against 96.24.21.0/24, and Chris will say, nope, that IP address for the corporate web server is not in my first entry's network. It'll go to the second one and say, is it part of that network? No, it's not part of that network either. We then get to the third entry, which is the default route. And John will say, Chris will say, off we send it to John. So it will forward that packet off to 96.24.21.5, which is John. And you can see Chris and John are in the same network. Chris is .4 and John is .5. So they share a local network. Chris will forward that packet over that network to John. John will do the same thing Chris did. We look at John's route table. John will look at the packet in the first entry and say, does this packet belong inside this network of 96.24.21.0/24? No, it doesn't. It doesn't belong in that network. That /24 is only 256 addresses, and 201.88.65.10 is not in that range. The second entry, though, is where it gets interesting. We can look at that entry at 201.88.65.0/24, and our packet absolutely fits in that. At .10, it is in that range from 0 to 255, and John will then spit the packet out NIC2, which is on that network. And if we look at John, we can see John's got 2 Ethernet cards, and NIC2 shares a local area network with the corporate web server. That is .10, and John in this case is .254 in that network, and the web server is .10. And I'm only talking about the last number, also called an octet in this case. But so when we look at that packet in John's route table, it will never reach the default route because there is a more specific route before it, and it will shoot it out NIC2 to the corporate web server. The corporate web server will deal with the request, and it will generate packets back to Kelly. It will use Kelly's address as the destination and its own address as the source. It'll generate packets, evaluate it against its route table, and begin to transmit packets where they need to go, and it'll follow the path back eventually to Chris, who will have a more specific route, just like when we went the other direction, and Chris will pass the packet on to Kelly. All right, and the last thing we're going to talk about, I'm going to update our example a little bit to add something that would be in most corporate networks and even in most home networks. We're going to add this concept of an outside world. What happens when Kelly wants to talk to Google or something that's not on the corporate network, and I want to talk to the global internet? That hasn't been part of our other examples, but I'm going to add it to this one so that we can have a little bigger discussion about how do I get to the internet when I don't know what to do with it. So the traffic we're examining will have a destination that's not set for anywhere inside our corporate network. And we're going to make changes to our corporate routers to have a default entry to route to our ISP, our internet service provider. And this is In my case at home, it would be Spectrum. At the university's case, it would be Ornet. But it would be the next order up provider that provides me probably with my IP addresses and definitely with my connection to the internet. We hand that traffic off to the ISP. We don't really know where it's going to go from there. That's partly the ISP's problem, and they work with a variety of different providers that handle the core of the internet to route that. And to sort of represent that in our diagrams, we use a picture of a cloud because a cloud icon is used either when we don't know the route that it's going to take, or the route might change over time. In an earlier lab, we talked about traceroute and how it would show all the different routers between a source and a destination. And the truth is, if you went and tracerouted over the series of a couple of days to the same locations, the intermediate hops might change. And that's not unusual. So again, we use a cloud because we're not in charge, or we're unable to know the path that it will exactly take, but we know it'll get to the outside world, and it'll eventually reach its destination. All right, so for the purpose of simplicity, I had to do a little editing to the diagram. I had to remove the circles, but it did leave the mini switches, and in this case I added a long haul fiber connection to represent our connection to our ISP, because oftentimes our ISP is not going to live within 100 meters of wherever our corporation is. We will have a fiber connection. Again, there'll be discussions about that perhaps in another video about how point-to-point or long-haul connections are done, but it's beyond the scope of this video. In terms of routing, it will work exactly the same as any of our mini switches in terms of how does the layer 3 IP address situation work. So you can see we've got on the left side, we've got Kelly sending a packet to Google, and it's a request for data from 8.8.8.8, which is one of Google's IP addresses, one of Google's many IP addresses. And again, Kelly's route table will look at it and say, gee, it's not part of my local network, so I'm not just going to release it out. I'm going to give it to my default router, which we're going to hand it to Chris at 45.65.22.254. Chris will look at it and we'll evaluate the packet on Chris's route table, where we'll go through all three of our original entries and decide that it's really not meant for us. Now you'll notice on Chris's route table I've actually added a new route entry for 102.88.65.0 that was not there before. However, the next hop and the default route both go to the same place. So while I have a more specific route, there may be times when I want to do other things with that kind of stuff. So I'm planning ahead by adding a more specific route when I know I want to go to the corporate web server in case Chris winds up having multiple connections to other networks as well. So I added a route entry there for that. Our packet in this case will go all the way through Chris's route table until it reaches the default route at the bottom, where we'll forward it on to John. Now so far this is just like our corporate web server discussion in the previous example. With the possible exception that I added a little bit to Chris's route table, but that's not meaningful for our debate and discussion here. John will receive the packet, and you'll notice I've added a third NIC for John. And John now has a connection to our ISP, which is on a third network. And the packet will go down the list here as it traverses down the list, and we'll notice that it doesn't match any of those first three packets. 8.8.8.8 is not part of the first three entries in John's route table, and eventually it will get to the default route entry at the bottom and go out to 98.75.54.254, which is our ISP, and we'll hand it off to our ISP. And at this point it's beyond our corporation's control to understand where it goes. We pay the ISP to handle that kind of traffic, and that's what they're paid to handle. They give us some IP address space to work with, and we give them our global internet traffic, and they handle it out to the larger internet and bring that responses back to us. And that's the cloud there for the ISP represents that. Google will respond through its networks, and it will bounce back eventually to our ISP, who will hand it back to John, and John will route it back to Kelly. I hope you've understood and enjoyed this tech nugget. Thanks for watching. We'll have more tech nuggets on more exciting topics, some of which we talked about in this video, and there'll be more on more exciting topics: firewalls, NATs, local area communication. Stay tuned.